defined for unit mass can be taken as intensive properties. The ratio of any two extensive properties is intensive. To check whether a given function is a thermodynamic property or not. A thermodynamic property is an exact differential. Check for exactness. If dz is equal to mdx plus ndy, where m and n are functions of x and y, dz is said to be exact differential if dou m by dou y at constant x is equal to dou n by dou x at constant y. Then dz is said to be exact differential and z is a thermodynamic property. For example, differential of PV product, where P is the pressure and V is the specific volume, can be written as PdV plus VdP. Here M is equal to P and N is equal to V. Then dou P by dou P at constant volume is 1 and dou V by dou V at constant pressure, it is also equal to 1. Hence the above equation is satisfied. It means dPV is exact differential, PV is a thermodynamic property. The PV product is also known as flow work or flow energy, which is a thermodynamic property. Please note that PdV and VdP, they are not thermodynamic properties. Similarly, heat and work, they are also not thermodynamic properties because they are never possessed by thermodynamic system. They are energies in transit or energies in exchange between system and surroundings via system boundary. Heat and work are energies in transit, hence they are path functions. Any thermodynamic property is point function, whereas heat and work are path functions. Next, coming to the thermodynamic state, it is the condition of system described by any two independent intensive properties. On a thermodynamic plane like pressure volume or temperature entropy, the thermodynamic state is indicated by a point. The state of a system is indicated by a point on any thermodynamic plane like PV plane or TS plane or pH plane, etc. Then coming to the change of state or thermodynamic process. Whenever a thermodynamic system undergoes a change of state, it is said to have undergone a thermodynamic process, which is represented by a thermodynamic path. In fact, a thermodynamic path is a series of states undergone by the system during the process. As shown in the figure, a thermodynamic path is indicated by a line joining of the series of states undergone by the system. Coming to the thermodynamic equilibrium. A thermodynamic equilibrium could be broadly seen as a combination of three equilibriums, namely thermal equilibrium, mechanical equilibrium, and chemical equilibrium. Thermal equilibrium means no temperature gradient between any two parts of system or between system and surroundings. Mechanical equilibrium means no pressure gradient or difference between any two parts of system or between system and surroundings. Chemical equilibrium means no change in chemical composition of system with respect to time, or otherwise there should not be any chemical reaction inside the system. Only when all the three equilibriums are satisfied, then only the system is said to be in a thermodynamic equilibrium. A state could be assigned to the system only when it is in a thermodynamic equilibrium. Then only it could be indicated on a thermodynamic plane. Next, coming to the quasi-static process, very important concept in thermodynamics. Whenever a system undergoes a change of state in such a way that the deviation of thermodynamic system from thermodynamic equilibrium is infinitesimally small, then such a change of state or process is known as quasi-static process. It takes infinite time to complete a quasi-static process, because during this process the gradient of any property is infinitely small. A quasi-static process is also known as a reversible process. Now let us define reversible and irreversible processes. A reversible process is that thermodynamic process which can proceed even in the reverse direction without leaving any proof or evidence that the process had ever occurred. A reversible process is that process which could proceed either in the forward direction or in the backward direction without leaving any process, any proof, without leaving any proof that the process had ever occurred. That means, for example, if A to B is a reversible process, then after reaching the state B, the system could proceed to A along the same path but in the reversed direction without leaving any proof or evidence that the process had ever occurred. That means if Q is the amount of heat supplied during the process A to B, then in the process B to A, the same amount of heat should be rejected. If similarly, if W is the work done by the system during the process A to B, the same amount of work should be rejected to the same amount of work should be done on the system in the reversed process B to A. Even the energy interactions must be reversed. Then only the process could be called as a reversible process. A reversible process should not involve any irreversibilities like mechanical friction, viscosity, electric resistance, turbulence, eddy currents, magnetic hysteresis, etc. Even heat transfer through a finite temperature difference is an example for irreversible process. A reversible process is only a hypothetical process or ideal process which is not practically feasible or possible. All practical or natural processes are irreversible. For example, heat transfer through a finite temperature difference. Work done by a closed system during a quasi-static or reversible process is given as integral P dV. which is equal to the area of PV curve on x-axis. Taking the PV plane, a path on PV plane, the area of the curve, this area is equal to work done by a closed system in a reversible process or quasi-static process. Definition of thermodynamic work. A positive thermodynamic work is said to be done by a system if the sole effect external to the system can be reduced to the raising of a weight. For example, if we take a car battery which has positive and negative terminals, a resistance is connected with a switch. When the switch is closed, current passes through the resistance and it is heated up. At the first instant, we think that there is no work done. But if the same system is reduced as shown in the second figure, the resistance is replaced by a motor and a pulley arrangement connected to a weight. If the switch is closed, current passes through the motor, pulley is rotated and the weight is lifted up. Hence, the effect external to the system is reduced to the raising of a weight. So, even in the first figure, when the switch is closed, when the current passes through the resistance, there is some positive work is said to be done by the battery. Work has two sign conventions, namely positive if done by the system, like expansion work done in the turbine by the fluid, and negative if work is done on the system, like compression work done on air in a compressor or blower. Coming to the sign convention for heat transfer, Q or heat is said to be positive if supplied to the system. Q is said to be negative if rejected from the system. Now, coming to the laws of thermodynamics, the fundamental concepts of thermodynamics. In total, we have three laws. Zeroth law of thermodynamics, which defines the temperature as a property. First law of thermodynamics, which defines internal energy as a property. And second law of thermodynamics, which defines entropy as a property. In fact, there is third law of thermodynamics also is there, which defines absolute entropy of a perfectly crystalline structured material at absolute temperature or 0 Kelvin. But the first three laws, that is zeroth law, first law and second law, are very important in our perspective of the subject. So let us state the zeroth law of thermodynamics. The law states that whenever two thermodynamic systems, namely A and B, are in thermal equilibrium with a third system C, then though two systems are in thermal equilibrium with each other. Thermal equilibrium means having the same temperature. For example, a human body is not in thermal equilibrium with its surroundings, because our human body is temperature is 37 Celsius, whereas the surrounding temperature is a function of time. Many a times human body temperature would not be equal to the surroundings temperature. Hence, human body is not in thermal equilibrium with its surroundings. As seen in the figure, if A and B are independently in thermal equilibrium with a third system C, it means A would be in thermal equilibrium with system B. All the three systems shall have same temperature. So temperature can be seen as a thermodynamic property which decides whether a particular thermodynamic system is in thermal equilibrium with its surroundings or not. Coming to the first law of thermodynamics, which is also known as law of conservation of energy. In principle, it is similar to the Bernoulli's theorem stated in fluid mechanics. In fact, in thermodynamics, the first law of thermodynamics can be seen as three different modules, namely, first law defined for cyclic process, then first law defined for non-cyclic process undergone by closed system, and third module is first law for steady flow open system. Let us take the first module, first law for thermodynamic cycle. Let me define first of all a thermodynamic cycle. Thermodynamic cycle. After undergoing various thermodynamic processes, if the system comes back to its initial state, it is said to have undergone a thermodynamic cycle. One to one is thermodynamic cycle. A cycle may have 2 processes, 3 processes or 4 number of processes. Most of our thermodynamic cycles do have 4 thermodynamic processes. Coming to the first law of a thermodynamic cycle, whenever a system undergoes a cyclic process, the net algebraic sum of heat transfers is directly proportional to the net algebraic sum of work transfers. Mathematically, cyclic integral of delta Q is equal to cyclic integral of delta W. This is the first law applied to the cyclic process. The circle in the integration means that all the heat transfers must be added up algebraically with the sign taken into account for the entire cyclic process. Similarly, the work transfers also must have to be added for the entire cycle, taking the sign into account. Both would be equal. The net heat transfer in the cycle should be equal to the net work transfer in the cycle. That is the first law of thermodynamics applied to the cyclic process.